So yes, I'm Peter Hanna. I'm a PhD student at Imperial College London, and the work that I'm doing currently is sponsored by Tata Steel. So we've seen a lot of welding two things to each other, or to the next thing. I'm going to discuss welding things to themselves. So Tata produces these squared hollow sections, which are done to the 10-10 standard. And so far, they've predominantly been used in construction, so very simple loading. And there is a weld down the length of them, a seam weld, and the aim of this project is to determine the fatigue behavior of this weld, and particularly the placement of the weld that we get. So in case you're unaware, these are made by high-frequency induction welding process. And so the way we get these is we take a big coil of steel, we fold it over on itself this way, use an induction coil, and the eddy currents in the edges of the steel heats it up very hot, and then you squeeze it together with the rollers. You then get a squeeze out the top and bottom, so you get a weld bead, and the default is to remove the external weld bead, and then there is the option of having the internal weld bead removed as well. Post-welding, they then take them through a furnace up to, say, 1200 degrees, and then form them in a normalizing range and allow them to normalize. So going straight into it, well, as I mentioned, we're looking at the placement of the weld, and so the proposed worst case scenario is having the weld in the corner. You can also have it on the face, and so on the left here we've got one where it's on the face and we've had both weld beads removed. On the right we have a corner weld where the internal weld bead has remained intact. We get this banded microstructure, which is quite typical of a hot rolled steel. And you can see in the welded region, we've had this squeeze, and you can see how it's all moved in that direction. And when it's in the corner, you get a much thinner weld section. One important thing to note is that here you get a couple of features on either side of the weld bead. And this is proposed to be, as it's pushed into the corner, we get some folding of the material. Moving on. So in order to start determining how the fatigue life is going to be affected, I started with some sort of simple mechanical tests. The first one was hardness testing. And so up here, we now have a post-weld but non-heat treated sample. You can see we've got quite a lot of recrystallization into the martensite phase within the weld region. And you can also see the weld line going up the middle. We then, after the recrystallization zone, we've got the thermomechanical zone and the heat affected zone. And so when we take a hardness map of this, you can see quite clearly you can just about see it on the edges here. These are our bulk material readings, which sit at around 150. And then within the welded region, we get to 450. So it's quite a stark difference. And you can just about see that we get some, you can see that we do get some differentiation between the two, or between the regions of the weld. Another just interesting thing to note is that when the bead is trimmed on the external surface, we seem to get some hardening effects at that point too. So if we now take a smaller section of this, and I've just reproduced this one here. So after it's normalized now, I took another map, and this is my data. So you can see we should have some weld lines, but we've got absolutely nothing. So if I just change the scale on this, you can see I've put in the weld there, and you can see we've got a very, very slight variation, slightly harder in the weld region, but largely speaking, we have a fairly homogeneous material, and so the material itself is unlikely to cause any significant issues in fatigue. I also did some tensile tests. These were taken through thickness. because as the tube cools, you're likely to get some quicker cooling on the outer surface, possibly a little bit quicker cooling on the inner. But then the middle, in theory, will be the slowest to cool, and so could have the largest grains, and so be a more ductile material. This is the orientation I took them out of, and so you can just see we took a little stack of 3 in each place. I then used DIC and a very small tensile test rig you can see there. And if we go to the next slide, this is my data. So just to explain, there's a lot of lines here. These ones around here and going over the top, essentially solid lines are unwelded material. Dashed lines are welded material. We've got some dotty in there just because the solid gray was hard to see. But you can see that essentially we've got the same elastic properties, pretty much the same yield points, and up to around the UTS, then it's all largely the same. Yes, there's some scatter, but that's to be expected from sort of small samples. The main difference is in the welded material, we do seem to have less ductility. And so this darker one is our internal surface. If I just go back. So the darkest lines are this one, and then the gray, and then the very light gray are the outside ones. And so the outer surfaces do seem to exhibit less ductility than the middle of the sample. If I then show you the welded samples themselves, we've actually got the weld running this way through them. And so you can see before test and during test. And this is my DIC that you can see. And we've got 2 bands down each side of the weld. And we do get, in each of these welded samples, we do get failure at the weld. So now going into some fatigue tests, or rather just before fatigue tests. I produced this fixture, which I could attach to my samples. This allowed it to be essentially loaded like a compact tension sample, except there's a lot more movement in this. It allowed for a unidirectional loading, which would mean that everything gets a lot simpler. My initial test was to take one of these. It does look like there's machining marks on this. There are for the actual samples. They were nicely polished and ground. So those were not detrimental to any of the tests. I then put a speckle pattern on it, did some more DIC, and just loaded it from 0 to 10 kilonewtons. At the end of that, you can just about see this is our weld bead that we saw before, and these are those 2 features. And so we do get some localized yielding around those features, which just confirms that these might be an issue when it comes to fatigue. Going on to my data then. So this is the DIC from that. This is a little bit after the sample has started to yield. I use that yield point as my absolute max. Do not go over this during the fatigue tests. And you can see that we do just about, it's not quite high enough resolution, but we do just about see that you can see the stress concentration on the sides of the weld in the DIC data. But what we see over here is we have our unwelded corners in red and our welded ones in black. And so there is a decrease in life from the corner weld. And if I go on, this is theorized to be because of these features. When we've had that squeeze, we get a lot of oxides in here, and we don't get full fusion of the material. And so the hope is, if you take off the internal weld bead, you'll get a nice smooth surface, and so we shouldn't get that squeeze. And so some of the future work is to test these, the trimmed ones, and hopefully it'll restore the fatigue life. Fatigue life back up to where it is for the unwelded sample. Another indication that these is, well, first off, I saw it on the fracture surface, but also Where is it? It's gone. The deviation from the log line there indicates that we have very little scatter, and crack initiation is a fairly unpredictable thing. And so having that deviation, or that little deviation, suggests that we're getting propagation of the crack, but not necessarily initiation. Right, next. So this is a very dark image now of my crack surface. The pink over that end, that is the outside of the weld bead. So if we go back, that's this section, you can just see that. We then get the green section is our unjoined material, which is this bit just here. Ooh. And then from this point onwards, this is our fatigue crack. And then this red bit here is our ductile tearing region. And so I did a very simple model, just 2D simulation. And so on the top, we get our plane stress, and on the bottom, we get our plane strain. And you can see that they line up with each of these points along the crack surface. And you can see that after we've got that ductile tearing start, you can see that we get plastic collapse in the back of the sample. I also did a purely elastic simulation and plotted my K1 and K2 from that for different crack lengths. And if we take these lines, you can see that the point at which they cross lines up reasonably well, around 4 millimeters, with the point at which we get ductile failure in the material. So next steps. This I can see that, or we can see that this is a crack propagation issue when we have the weld bead untrimmed. And so I'm going to do a study into the crack growth rate characteristics of this material. I've just put on here a couple places where that material could come from. I'm also going to try and improve my simulation, get it to actually, because currently it's just, it's several simulations at different crack lengths, whereas it would be nice to have one that actually propagates the crack through. And then I also want to test the trimmed sample in the corner to see if, or to ascertain that it is a geometric impact on the fatigue life rather than a material one. So just to conclude, these tubes are going to be are needed in a more mechanically stringent market. They have more dynamic loading on them. I tested the hardness, and I took samples of the corner with the welding and determined the fatigue life of those. We found fatigue life decreasing features around the weld bead. And finally, I'm going to do some crack growth analysis on as my future work. Thank you very much.